In this session, I'd like to introduce the important theorems, Virial theorems. This is a theorem to relate the gravitational potential energy with the internal energy. So we use a hydrostatic equilibriums. This is the equation. Instead of R, we use the M as the independent variables. Then you can multiply the V in the both sides and then integrate over the M. So V is equal expressed 4 pi r cube over 3. This V is expressed in the case of the spheres. We use the spherical symmetries. So V equal 4 pi r cube over 3. And then integrate over the dm. So we have this equation over the whole stars. Then by the right hand side, this is equal to the right hand side. Right hand side can be expressed. Actually the 4 pi is going to be cancelled out. Becomes cancel. Omega, definition of the omega is a minus 0 capital M Gm over R dm. So using this definition of the omega, gravitational potential energies, right hand side is expressed 1 over 3 omega. And the left hand side, this is left hand side. This is left hand side, this is right hand side, is expressed same equations. Then integration by part. You are going to apply, this is integration by part. Then at the centers, PC is the pressure at the centers. At the centers, actually volume is 0. And then pressure is 0. So this means pressure at the surface. This is surface. Pressure is 0. So the first term is become 0. So right hand side equal to the left hand side, it becomes this equation. So actually the density times the volume, it becomes a dm. So we use this equation applied to the here. Then the equations can be expressed in these equations. And right hand side is a gravitational potential energy. And the left hand side, internal energies. So I'd like to show you. When we consider the ideal gas, equation of state is expressed P pressure is equal to the density over m sub g is the mass of the nucleus times K is the Boltzmann constant and the T is the temperatures. And the kinetic energy per particles. We don't consider the molecules. In the case of the nucleus, we only consider translational energy. This is equal to 3 times 1 over 2 kT. So each directions, we have a 3D motions because x, y, d, z. So you have to multiply the 3. So it becomes 3 over 2 times kT. Then kinetic energy per unit mass. If you divide it by the mg, this quantity, we could calculate determine the kinetic energy per unit mass. And then using this equation of state, kT over mg is here. So this is going to be expressed 3 over 2 p over rho. To find out internal energy of the stars, internal energy of star, you have to integrate over the whole stars. Integrate 0 to the capital M is the total mass of a stars. Then you can substitute this equation here. It becomes 3 over 2, 0 to the M, P over rho dm. So we have already discovered the last slide. Integration, it becomes minus 3 times this quantity is omega. So you can use expressions here. It becomes minus 1 over 2 omegas. So we have a really important equations. Internal energy is related to gravitational potential energy in the stars. So using the Virial theorems, we'd like to estimate average temperature of stars. But first of all, we'd like to calculate gravitational potential energy of omega. In the case of the really simple case, uniform density. So in this case, the density is constant. So rho is constant. So in this case, total mass is expressed density times 4 pi over 3. Capital R is a radius of a stars. Then omega, gravitational potential energy, is expressed minus gm over r dm. And to calculate these quantities, r is a function. This is quite difficult to perform these integrals. But in the case of the uniform densities, you can just calculate this quantity is minus rho squares 0 to the r g 4 pi r cube over 3 over r, and the dm is a 4 pi r square dr times rho. So then we could perform these integrals. It becomes minus 3 over 5 g m total mass squares over radius of the stars. So we could express the minus alpha gm square over radius of a stars. In the case of the uniform density, this alpha is 3 over 5. So in general, we'd like to express the gravitational potential energy of a stars is expressed the same equations. But in this case, instead of the 3 over 5, we use alpha. But alpha is the order of ones. Then we'd like to estimate the internal energy of a stars using these equations. So we introduce the average temperature of the stars. This T bar is defined 0m T dm over total mass. Then using the Virial theorems, you can substitute U is here and omega is here. Average temperature of a stars. So in this case, you can substitute alpha is 0.5 and m is a mass of the suns and r is a radius of the suns, and the average temperatures becomes about 4 million kelvins. This is much higher than the surface temperature of the sun is 6,000 kelvins. So temperature is increasing inward. So if you consider the ionizations of hydrogen atoms, hydrogen H is composed of the protons and the single electrons. Ionization meaning the proton loses the electrons. Electron is moving away. Ionization temperature for the hydrogen atom. Hydrogen is the most abundant element in the suns. So this ionization temperature is 10,000 Kelvin. So this 10,000 Kelvin is much lower than the 4 million Kelvin. Average temperature of the sun, we actually estimate average temperature of our stars. So because of the high average temperatures, we considered completely ionized inside of a stars. So composition of the star is composed of the nucleus and the electrons. Okay, so this is the end of this session.